Metatiling selection algorithm. A limiting factor when choosing the metatiling size is the overhead and memory consumption required to generate the map image. For example, by default the maximum amount of memory that a single request is allowed to use in GeoServer is 16 megabytes, which are sufficient to render a 2048 by 2048 image at 4 bytes per pixel, or a 8 by 8 metatile of standard 256 by 256 pixel tiles. Table shows the maximum gain that can be achieved by the use of metatiling techniques. This maximum gain occurs when the whole metatile is used to cache new tiles that were not yet cached. While this is the case when automatically seeding tiles in sequential order with non-overlapping metatiles from an empty cache or in the early startup of the service, it would be useful to evaluate metatiling in the most general scenario where the cache is partially filled. In that case, each metatile is likely to add redundant information, since it is probable that some of the tiles encompassed by the metatile were already cached, thus reducing the effective gain of this method. The performance of metatiling during dynamic cache population with users' requests has been evaluated using the Recency-based cache, described in section. Simulations were driven by trace files from the public WMS tiled web map service of Cartography. Being traces recorded in a real, working system, these logs represent a more realistic pattern of user behavior than a synthetic pattern. The Corin WMS service was used as remote backend. Cache hit ratios obtained for different buffer sizes and metatiling configurations. Number of cache tiles for different buffer sizes and metatiling configurations. A total of 1.000.000 requests were made to the cache. The experiment was repeated for different metatiling configurations. For each configuration, the cache hit ratio and the number of cache tiles after task completion have been collected, starting from an empty cache. Results are shown in AND. As can be shown, both the cache hit ratio and the number of cache tiles grow with the buffer size. For a fixed buffer size, both metatiling strategies, centered and minimum correlation, obtain similar results. However, the number of cached objects is significantly improved with the minimum correlation configuration. The improvement increases with the metatiling size. Thus, the advantage achieved with the minimum correlation metatiling configuration is that, maintaining the cache misses, and therefore maintaining the number of requests to the remote WMS server, a broadened population of the cache is achieved. These extra pre-generated map image tiles stored in the cache will allow a faster delivery of future requests. When the tile cache runs out of space, it is necessary to determine which tiles should be replaced by the new ones. Most important characteristics of web objects, used to determine candidate objects to evict in web cache replacement strategies, are recency time since the last reference to the object, frequency number of times the object has been requested, size of the web object and cost of fetch the object from its origin server. These properties classifies replacement strategies as recency-based, frequency-based, recency/frequency-based, function-based and randomized strategies. Recency-based strategies exploit the temporal locality of reference observed in web requests, being usually extensions of the well-known LRU strategy, which removes the least recently referenced object. Another popular recency-based method is the pyramidal selection scheme, PSS. Frequency-based strategies rely on the fact that popularity of web objects is related to their frequency values, and are built around the LFU strategy, which removes the least frequently requested object. Recency/frequency-based strategies combine both, recency and frequency information, to take replacement decisions. Function-based strategies employ a general function of several parameters to make decisions of which object to evict from the cache. This is the case of GD size, GDSF and least unified value, LUV. Randomized strategies use a non-deterministic approach to randomly select a candidate object for replacement. For a further background, a comprehensive survey of web cache replacement strategies is presented in. According to that work, algorithms like GD size, GDSF, LUV and PSS were considered good enough for caching needs at the time it was published in 2003. However, the explosion of web map traffic did not happen until a few years later. In this section, we propose a cache replacement algorithm that uses a neural network to estimate the probability of a tile request occurring before a certain period of time, based on the previously discussed properties of tile requests, recency of reference, frequency of reference, and size of the reference tile. Those tiles that are not likely to be requested shortly are considered as good candidates for replacement. The use of neural networks for cache replacement was first introduced by Gilad, with the Cora algorithm. Cora uses backpropagation neural network for the purpose of guiding the line/block replacement decisions in cache. The algorithm identifies and subsequently discards the dead lines in cache memories. It is based on previous work by, who suggested the use of a shadow directory in order to look at a longer history when making decisions with LRU. Later, an improved version of the former, Cora 2, was proposed. Other algorithms based on Cora were also proposed. A survey on applications of neural networks and evolutionary techniques in web caching can be found in, proposes the use of a backpropagation neural network in a web proxy cache for taking replacement decisions. A predictor that learns the patterns of web pages and predicts the future accesses is presented in. Discusses the use of neural networks to support the adaptivity of the class-based least recently used, CLRU, caching algorithm. Artificial neural networks, ANNs, are inspired by the observation that biological learning systems are composed of very complex webs of interconnected neurons. In the same way, ANNs are built out of a densely interconnected group of units. Each artificial neuron takes a number of real-valued inputs, representing the one or more dendrites, and calculates a linear combination of these inputs. The sum is then passed through a nonlinear function, known as activation function or transfer function, which outputs a single real value, as shown in artificial neuron. In this work, a special class of layered feed-forward network known as multi-layer perceptron, MLP, has been used, where units at each layer are connected to all units from the preceding layer. It has an input layer with 3 inputs, 2 hidden layers each one comprised of 3 hidden nodes, and a single output. According to the standard convention, it can be labeled as a 3/3/3/1 network. It is known that any function can be approximated to arbitrary accuracy by a network with 3 layers of units. Learning an artificial neuron involves choosing values for the weights so the desired output is obtained for the given inputs. Network weights are adjusted through supervised learning using subsets of the trace data sets, where the classification output of each request is known. Backpropagation with momentum is the used algorithm for training. The parameters used for the proposed neural network are summarized in table. Proposed 2 hidden layer feed-forward artificial neural network. Neural network parameters. The neural network inputs are 3 properties of tile requests: recency of reference, frequency of reference, and the size of the reference tile. These properties are known to be important in web proxy caching to determine object cacheability. Inputs are normalized so that all values fall into the interval, by using a simple linear scaling of data as shown in equation, where x and y are respectively the data values before and after normalization. Xmin and Xmax are the minimum and maximum values found in data, and Ymax and Ymin define normalized intervals so Ymin less than or equal to y less than or equal to Ymax. This can speed up learning for many networks. Recency values for each process tile request are computed as the amount of time since the previous request of that tile was made. Recency values calculated this way do not address the case when a tile is requested for the first time. Moreover, measured recency values could be too disparate to be reflected in a linear scale. To address this problem, a sliding window is considered around the time when each request is made, as done in. With the use of this sliding window, recency values are computed as shown in equation, where delta t is the time since that tile was last requested. Recency values calculated that way can already be normalized as stated before in equation. Frequency values are computed as follows. For a given request, if a previous request of the same tile was received inside the window, its frequency value is incremented by 1. Otherwise, frequency value is divided by the number of windows it is away from. This is reflected in equation. Size input is directly extracted from server logs. As opposite to conventional web proxies where requested object sizes can be very heterogeneous, in a web map all objects are image tiles with the same dimensions, typically 256 by 256 pixels.